right, we're going to talk about air-sea interaction. Now, I'm an oceanographer and I know a lot about the ocean, but I'm not a meteorologist, but I have to know a whole lot about the atmosphere because the ocean and the atmosphere work together so closely. They're interlinked. You can't know about one without knowing about the other. All right, the sun is the ultimate energy source. Remember that external energy source, the sun, is what drives atmospheric motion and oceanic motion, so winds and ocean surface currents. And what causes these motions are the fact that parts of the Earth receive more sunlight than other parts of the Earth, so there is an unequal heating. And because of this unequal heating of the Earth and the Earth's wonderful ability to try to distribute that energy in an even way through atmospheric circulation and ocean currents, we're going to talk a little bit more about that. It's pretty important. So the Earth is a sphere. Okay, that's not really a big shock. The Earth is tilted on its axis, and I believe we talked about that in the first week or two when we talked about how the moon was formed, and probably that impact that formed the moon caused the Earth to be tilted on its axis. Because the Earth is tilted on its axis is the whole reason that we have seasons. Okay, it doesn't have to do with how far or how close you are to the sun. It has to do with which hemisphere is pointed more directly at the sun. All right, solar energy is really concentrated between the tropics. Remember, the Tropic of Cancer is up in the northern hemisphere about 23 degrees north. The Tropic of Capricorn down in the southern hemisphere about 23 degrees south latitude. Those are the places where the sun is directly overhead during what's called the summer solstice. So, June 21st, it's going to be directly overhead 23 degrees north latitude. Then on our winter solstice, which would be the summer solstice for the southern hemisphere, it'll be directly overhead of the Tropic of Capricorn down at 23 degrees south latitude. So the sun basically, its direct rays are concentrated between the tropics and including the equator. So what that's kind of like is just think about somebody who has a very strong flashlight. If they flash it right in your eyes, it blinds you. But if they were to kind of flash it at an angle or even flash it up off the ground and have that light reflect into your face, it wouldn't be so bright. So I'm going to show you a slide. We're going to talk a little bit about some of these different properties, about how solar radiation is more spread out in the higher latitudes. More is reflected because the angle is not like a 90-degree angle. The straightest the straightest line between 2 points is a straight line, and something called albedo or reflectivity. All right, check out this slide. This slide's pretty cool. Now, solar radiation is all coming in. See the yellow rays? We could actually have a bunch of those all coming in parallel from the sun. The sun is very far away and it's very large. So all that energy hits us in those parallel lines. Now, because the Earth is a sphere, you can see that it's going to be hitting the Earth's surface at the equator in this picture at a 90-degree angle. And so that's kind of like getting that flashlight flash in your eyes, straight on. That energy is really concentrated over a much smaller area. You can see the line that represents the atmosphere, and what happens is the atmosphere can reflect solar radiation. It can also absorb solar radiation. So what you want is solar radiation to be passing through as little atmosphere as possible and at a 90-degree angle in order to make the most amount of that solar radiation hit the Earth. Now look at the higher latitude. That's, I don't know, 65, let's call it. North latitude up there. Now it's hitting at the Earth at an angle. So what sunlight makes it to the Earth, first of all, it's going to be spread over a much larger area. I've got another slide that'll show you that. A lot more is going to be reflected. Now let's look at the atmosphere. It's passing through a lot more atmosphere, and it's passing through that atmosphere at an angle. So more will be reflected there. All right, here's that slide that I promised you that kind of shows you that, the solar radiation is really concentrated where it's hitting at a 90-degree angle. And then look at it, it's probably 3 or 4 times as much area. The same amount of solar radiation is going to be spread over. Now, if you were using a magnifying glass and trying to start a fire using the sun's radiation, you got to get it in a certain way to make it hot enough. You got to concentrate the solar radiation. And that would be more like this bottom picture. If you don't put it over a really concentrated area, if you spread it out too big, yeah, you might warm it up a little bit, but you're not going to have enough power to start a fire. Now, just another quick thing is you guys think about where snow and ice are concentrated. They're concentrated in the higher latitudes. And so not only are we going to have more reflected solar energy when it hits the Earth, but because of the tilt there, but also because white is reflective. They say on a hot day, don't wear a black shirt, wear a white shirt. You want to walk on white sand on a hot day, not black sand. It'll burn your feet. Because dark colors will absorb heat and white colors will reflect heat. And so a lot more is reflected. That's called albedo or reflectivity. All right, well, here's some actual data that supports what I've been telling you. Remember when the sun was coming in at a 90-degree angle of the solar energy that makes it to the Earth's surface, 98% is absorbed and only 2% is reflected. Well, let's go up to a higher latitude now, far right. Sunlight can come in at a 5-degree angle. And, first of all, the atmosphere is going to absorb a lot and reflect a lot. And of that less energy that comes in is spread over such a much larger area, 60% of that lower energy level will be absorbed, while 40% is reflected from the Earth's surface. So the sun directly overhead means much more solar energy is being received in that area. All right, Earth seasons, you guys, you got to understand this. This is one of those questions I probably will ask, and it's amazing how very educated people can be really wrong. Now, the Earth seasons have nothing to do with how close or how far to the sun we are. In fact, we are closest to the sun in January, and that's certainly not our summer. It has to do with which hemisphere is tilted towards the sun and receiving more direct sunlight. Okay, so let's look at a picture there. Well, I've got a picture coming up here. So the Earth does go around the sun in an elliptical orbit, and there are times when we're closer or farther from the sun, and that will affect our tides. The highest high tides that we have and the lowest lows are typically in January. The Earth is tilted on its axis, and alternatively, either the northern hemisphere during our summer is tilted towards the sun, or during our winter, it's the southern hemisphere that's tilted towards the sun. Okay, when you're tilted towards the sun, you're receiving more direct sunlight and more hours of sunlight. And so, over a 1-year cycle, the Earth will keep going around the sun, and at different times, the sun will be concentrated either in the northern hemisphere from the tropic or down to the southern hemisphere from that tropic. So the areas between the tropic, including the equator, receive the most solar energy on a year-to-year basis, or always. So here's the picture. So let's start at the summer solstice on the far left. Now look at the bottom picture. You can see there's the northern hemisphere. You guys can see Australia down in the southern hemisphere. So in our northern hemisphere summer, you can see that the northern hemisphere is pointed towards the sun, and so what it's receiving is more direct sunlight. Now if you look at Australia during the same time, it's receiving sunlight at a lower angle, and so more of it's being absorbed by the atmosphere, reflected by the atmosphere, and actually reflected by the surface of the Earth, and so you're receiving less solar energy, therefore it's colder. All right, let's go over to the northern hemisphere winter or the southern hemisphere summer. You can see now, look at Australia. It's receiving that really direct sunlight, whereas the northern hemisphere is receiving the lower amounts of energy. Now, in the autumnal equinox and the vernal equinox, those are times when the sun is directly overhead of the equator. So, the equator is kind of getting a double dip of super energy. So sunlight is concentrated between the tropics and including the equator. And that's going to be the area of the Earth that will receive the most solar energy. Now, if you think about that, the Earth should get hotter and hotter and hotter there, where the rest of it gets colder and colder and colder. And the whole point is this idea of energy transfer, that the Earth has this beautiful method through atmospheric circulation and oceanic circulation of taking excess solar radiation from the low latitudes and transferring it up to the high latitudes. And like I said before, in economics, this would be like the perfect trickle-down theory. And in economics, that's where the rich give enough money that the poor are never poor. Doesn't work in our economy, right? But here, before humans messed things up, the Earth was actually pretty good at that. All right, now we got to just talk about the Arctic and the Antarctic summers and winters. If you guys go up to Alaska in the summer, you might say, wow, it was daylight 23 hours or 22 hours a day. But what you're going to notice is kind of like, yeah, you're going to have a day and you're going to have a dusk. It's not super bright sunlight. It's pretty weak sunlight, but it is still, like kind of like dusk, sunset time. And then during their winter, they're going to have almost 24 hours of complete darkness. Now, there used to be a really cool video, and I can't find it, but it was basically a time-lapse film of the longest day of the year at Antarctica. And you don't look directly overhead for the sun. The sun is actually practically at the horizon, and then you just kind of watch it go around because of this time-lapse film. And yeah, it's up 24 hours, but it's way low. So that angle is really low that the sunlight's hitting, and most of it's being reflected, and then most of it's being reflected by all that ice too. Now, those 3 months of daylight in both the northern and southern polar regions are enough to really set off the photosynthetic organisms in the ocean. And when the base of the food chain is happy, the rest of the food chain is happy. You guys know that the whales migrate to the Arctic Circle in the winter or in the summer months here. And what they're doing is, they're filling up on basically the buffet's open, the base of the food chain's happy, the rest of the food chain's happy, and they put on enough fat to kind of keep them going for a long time. And so it's worth that many thousand-mile migration. All right, so the solar energy is concentrated between the tropics, including the equator, and luckily the Earth is very good at transferring this heat. All right, so net heat gain, you can see this area. It's basically 38 degrees north latitude to about 38 degrees south latitude are areas of excess energy. That means that, actually, you guys, Rockland campus is at 38 degrees north latitude. That's kind of exciting because we're right on that cusp. So that means that if you go up north of us, to Oregon, they're in an area of net heat loss. But, up until recently, over the years, things aren't getting hotter or colder. They were staying pretty stable because the Earth is really good at transferring energy from these areas of net excess and basically equilibrium. It's called equilibrium, equalizing things out. Obviously, the tropics and equator stay warmer, but they don't get hotter and hotter and hotter every year, typically. Okay, so I got to keep going about these human things. We're really messing things up, but in the past, the Earth was just this perfect, balanced system. So we're going to talk a little bit more about transfer of heat. Now, about 2/3 of that transfer of heat happens because of air circulation, wind belts and boundaries. So we're going to talk about wind belts. And then about 1/3 of it is through oceanic currents. We're going to talk about hot currents, warm currents, cold currents, etc. And these are going to be the ways that we take that net excess energy from the warmer latitudes and transfer it up to the cooler latitudes. All right, so here's that nice diagram that shows that 38 degrees. Remember, that's where the Rockland campus, that's kind of shocking to me. That's very weird. We're right on the cusp of where we kind of receive the same amount of energy as we lose. And so this just beautiful balanced system of transferring heat between the areas of net excess and the areas of net heat loss. All right, so let's learn about the atmosphere a little bit. Now, you guys, we did talk about this before when we were in that first section, and we talked about how Earth's atmosphere evolved over time. Nitrogen is our main gas, and nitrogen's always been the main gas in the atmosphere. Remember, that's coming out of volcanoes. Now, oxygen is not new. I mean, it's been around for, 2.5 billion years in the atmosphere, or more than that. Remember, that is the product of photosynthesis. It was a waste product. So 78% nitrogen, 21% oxygen. So that leaves less than 1%, and we have about 0.9% of argon. Argon is a noble gas. It's that hermit gas that doesn't want to react with anything because its outermost electron shells are full. So we pretty much ignore that. But it's the next gas, carbon dioxide. That is very much a concern because this, even though it's 4/100%, and a lot of students go, what, 4/100%, and I'm worried, and yeah, you should be worried because in your parents' lifetime it's doubled, and they, if we keep going the way we're going, it's going to triple in your lifetime. And it's kind of like that old story, that straw that broke the camel's back. we don't know what that number has to be before the Earth kind of goes into a tailspin, before our atmosphere kind of loses it, because carbon dioxide, we're going to learn later on, is a greenhouse gas, and it holds on to heat energy, and it's one of the global warming gases. It's kind of bad news. So that number is a concern. A lot of naysayers say things like, oh, well, in the past, carbon dioxide was much more concentrated, and they're right. But that was, 4.5 billion years ago to 3 billion years ago or something like that, and it took billions of years to change the percentages, and to have this happen over 50 years in a human lifetime, I mean, that's scary. Okay, I'm so used to talking about millions, hundreds of millions, and even billion years that talking about 50 years, it's too fast, and it is because of us. All right, we got to talk a little bit about atmospheric pressure. Now, you guys know that, sometimes you say, oh, my ears pop. That has to do with changes in atmospheric pressure and trying to equilibrate or go into equilibrium with the pressure inside your ear and the pressure outside your ear. Atmospheric pressure at sea level, the average is typically what we call 1 atmosphere, or in metric system, 1,000 millibars. And what that represents is the weight of air in that air column in the atmosphere above you. And so every square inch of your skin has almost 15 pounds of weight on it. This is why, in order for us to walk on land and be erect, we have to have pretty strong muscles and good muscle attachments to our bones. And so, it's pretty amazing. It has to do with evolution and stuff. When those organisms crawled out on the land from the ocean, which is so supporting, a lot of things had to change anatomically. All right, you do know that, if you go up in an airplane, they always start the tour with hey, if the pressure drops, or, if they have a decompression event, that the air masks fall out, because if you're high enough, you can die. There's not enough oxygen up there for you, and you'll die, you'll suffocate. So it's kind of nice, and we know from recent events that actually works, and the air masks do fall down, which is good news. If you climb Mount Everest, we'll show you a picture here in a second, a lot of the people actually have to use supplemental oxygen, and some people died just because of that lack of oxygen. So most of the atmospheric gases are concentrated in the lower part of our atmosphere. Okay, so let's check this out. So here we are, and this is the pressure, and you know that pressures decrease when you're going up in an airplane, and that's why small airplanes that are usually not pressurized must stay below a certain amount. Otherwise, you have to breathe supplemental oxygen and have a pressurized airplane. And that's why the air masks fall when you're flying at, let's say, I don't know, 37,000 feet would be something like 8 miles or something. So that's where your airplane's flying. And so it's flying up where there's not enough oxygen to keep you alive. So, the amount of gases is much decreased the higher up you go. All right, we're going to learn a little bit about the different layers of the atmosphere. And really, I only care about 2 here. The troposphere. Most of us will never leave the troposphere. We're pretty much stuck here. Unless you're an astronaut or a Navy test pilot or something like that, you're really never going to leave the troposphere. Now, all of you guys have been in airplanes and you felt turbulence. You only feel turbulence in the troposphere. That's where all weather and circulation is happening. Once you get up into that stratosphere, there is no bumping, there is no turbulence, there is no circulation. You can notice that as you go up in elevation that the temperature drops, and that's true if you're in a small plane. I don't care if it's a hot summer day, take a jacket, because if that plane is not, got a pressurized cabin, there's obviously only a certain height you can go to, but it gets cold up there. All right. Then what you're going to notice is that when you go into the stratosphere, when you get to the top of the troposphere, you get into the stratosphere, it starts to heat up. That has to do with the topmost layer of the stratosphere called the ozone layer. Ozone's our friend. Ozone is a superhero, and there was a time in our past where we abused that layer, and that layer started to break down, and people were getting skin cancer, going blind, etc. And luckily, in my generation, people fixed this problem, or are well on the way of fixing this problem. So I have hope, you guys. I have hope that we can fix our climate problems because I saw this happen. Ozone is O3. I've got another slide. We'll talk about it. So oxygen, 3 atoms of oxygen together. You and I breathe O2. And in fact, ozone in the troposphere is bad. That's a smog thing. Your car gets smogged, and make sure you're not putting out ozone. That ozone up in the ozone layer, top of the stratosphere, is produced up there, and it protects us from UV radiation. So it is very, very important. All right, again, why is the temperature rising? Because that UV radiation that's being absorbed by the ozone layer, it heats it up. So it does make it warmer. And they just keep talking about this future travel of supersonic jets up in the stratosphere. It could take you an hour to get from New York to London or something like that. And it's possible. You can travel super fast, faster than the speed of sound. You don't have to worry about any turbulence or anything until you come back down in the troposphere. So the travel would be a lot faster. So maybe in your lifetime. All right, ozone, O3. It's formed up in that layer. So ozone that's formed in the troposphere does not leak up into the ozone. Don't think that your gross polluter old junker car is helping the ozone hole. It's not. It's actually causing global warming. That UV radiation actually that hits the Earth or hits the top of the stratosphere helps to produce that O3. And what was happening is that back in the past we had human-created chemicals that were called chlorofluorocarbons, CFCs, and they were propellants and refrigerants. So your hairspray, Pam cooking spray, your refrigerator, your car's air conditioning unit all had these in it, and they leaked like crazy because we weren't very careful about them. And hairspray, hello. And they went up. These actually did leak up into the stratosphere, and they blocked the ozone formation. So we had big holes over especially the southern hemisphere. So people that were living in southernmost South America were going blind, having terrible skin cancer, and that's how we kind of discovered it. And so the United States being the biggest polluter, we're always the biggest polluter, well, not always, but we have been up till now, we stopped it. If you have your air conditioning worked on or your refrigerator needs to be disposed of, there's special ways they do it so that the CFCs don't get out into the atmosphere. Plus, your hairspray and your Pam cooking spray, look at them. They probably say contains no CFCs because CFCs are also a propellant. All right, we are going to talk more about convection and density. And like I put the little note there, you knew it wasn't going away because, man, density makes the Earth work. Now, we're going to talk about convection currents in the atmosphere, and we're going to talk about small scale. I've got a convection current going on in this room right here. If you had a ground heater, one of those little vents that come out of the ground, I used to have a room just like this. And right where the radiator is, it had a vent that blew hot air. So the hot air, being less dense, would rise up. It would move along the ceiling, and then it would get near the cold part of the room, and it would cool down, become more dense, and then sink down. And I could actually blow up a balloon, put it over the hot air radiator, heat it up, expand it a little bit, and I could get a balloon moving around my room just like that. Okay, so here it is on a small scale. Now, we have it on a slightly larger scale. You know that during the summer, sometimes we get thunderheads and things. And that's because the air that's in contact with the Earth, it heats up. Because in the summer, the Earth is going to heat up quite fast in the northern hemisphere in our summer. And so it expands and it rises up. Well, as it rises up, it cools. And also, as it expands, it cools. And once that happens, it starts to cool, compress, contract, and fall back down. So kind of that up arrow is what forms our thunderheads that sometimes build up in the late afternoons. So here's a convection current happening on a slightly larger scale. But we're going to make the scale a little bit larger. It's going to encompass 30 degrees of latitude here pretty soon. But let's talk about a couple more properties that might make your air mass more or less dense. And that's water vapor. Now, you guys remember that your atmosphere is mainly N2 and O2. Now, water is H2O or HOH. And actually, the more water vapor that an air mass contains, the less dense it is. Because if you pull out your periodic chart of the elements, N2 and O2 weigh more than H2O. Okay, so warm air can hold more water vapor. That's why, typically when it's hot and humid. And that actually produces less dense air. So less dense air is going to rise up. Okay, and so humid, hot, warm air that's wet will rise up. Now, cool air cannot hold as much water vapor, and so it typically is pretty dry, and it's typically pretty dense, and it sinks. And so we're going to see areas where humid, warm, wet air is going to rise up because it's less dense, and cold, dry air is going to fall down because it's more dense. All right, we're on our way to making this convection current a little bit larger, and we're going to tie this into atmospheric pressure. Now, you guys have all watched the weather, and if they say a low is coming in, you know there's a storm. And if they say a high is coming in the summer, that means some pretty hot temperatures. Actually, in the winter, it means some very cold temperatures because we don't have that cloud cover to keep in the heat generated by the Earth, and so it can actually be the coldest parts of our winter when we actually have a high, and it can be the hottest parts of our summer. When you have a low, that means that warm air is rising up. Where you have a high, cold, dry air is sinking. Now, think about population density. I think we all learn about that. I live up in Auburn, which has low population density. I don't live in Sacramento, which the city would have high population density. So check out those pictures in the bottom, the little boxes. On the right-hand side, you have low population density. On the left-hand side, you have high population density. And this is actually low density air on the right and high density air on the left. That's exactly what it looks like. When it's less dense, it's going to rise up. Where it's more dense, it weighs more for that same volume, and so it's going to sink down. So low pressure regions are where warm air is rising, and it rises because it's less dense, and high pressures is where dry air is sinking. Okay, and you can see that difference in density. All right, just to kind of blow it up a little bit more, because we're going to, this is all happening in the troposphere. You can see that layer. And we're just going to kind of talk about this, and we're going to create this, this convection current, this circulation pattern. Now, another thing that's kind of interesting, you guys, is that when air expands, it cools. And if you, let some air out of your bike tire, okay, feel that air coming out, it's cold. Now, if you pump your bike tire up, a lot of times it heats up, especially if you have one of those road bikes that has really high pressure tires. And that's because when you compress air, it actually heats. And so when the cool air sinks, that compression actually heats it up. And when that warm air rises, the expansion actually cools it down. It's something kind of cool. It's a physics thing. All right, we got to talk about winds, and I can watch the news channel. I can turn off the sound. I can watch the weather channel, and I can tell you how the weather's going to be, and I can tell you which way the winds are going to blow. And this is important. First of all, I don't like wind that much, but if you have to go camping, it'll help you figure out, okay, which way the wind's coming, and how strong is it going to be, and where do I set up my tent, and maybe do I change my plans? Do I bring a kite? I don't know. But wind always blows from high to low. Now, if you remember that previous picture, you saw the high density and the low density. And all that means, it's kind of a chemical thing. It's equilibrium. It's trying to become equal. It wants, the amount of molecules in both those boxes to be equal. And the only way that can happen is if some of the ones from the high pressure area move to the low pressure area. So you guys, you got to remember this. Wind always blows from high to low. So if you're watching the Weather Channel and you see an H and an L, you know exactly which way the wind's going to blow. Never, ever blows from low to high. That's against physics. All right, moving air is called wind. And just remember, why do we have these differences? We have the differences because of differences in temperature, water content, water vapor content. That changes your density. You can just measure, you can pull up some data online, look at the millibars or the atmospheric pressure, and you can tell exactly which way the wind's going to blow. All right, we got to talk about the Coriolis effect. And the Coriolis effect, first of all, it is not a force. It's an effect. It only works on things that are already in motion, but it will deflect them. When I was young, I was very lucky, and I got to go on semester at sea. My dad's a professor, and everybody's like, "Oh, you're going to cross the equator. You're going to go to the southern, South America. Flush the toilet. Tell me about it." And it's like, what? And that's because, first of all, you guys, toilets are designed to suck large amounts of stuff down, and so there's actually a siphon, and it's not going to work. But if you do get water naturally circulating, it will circulate in a clockwise pattern in the northern hemisphere and a counterclockwise pattern in the southern hemisphere. And that is because of this thing called the Coriolis effect. So they're not quite right when they talk about toilets, but you know what? I get it. All right, it's a result of the fact that the Earth is a sphere, and that it's rotating, and the Earth is rotating to the east. Now, the Coriolis effect works on all objects that are moving up and down latitudinally on the Earth. If something is just moving along the same latitude, if we flew from someplace on the equator to someplace else on the equator and just flew along the equator, we wouldn't have to worry about it. But if we flew from the equator to Northern California, the Coriolis effect will affect us. Okay, now another rule you guys have to remember is that the curvature or the offset is to the right in the northern hemisphere. And if you think about it, you take a right, you're going in a clockwise pattern. And in the southern hemisphere, it's to the left. So if you take a left, 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 you're going in a counterclockwise pattern. I'll show you a little bit more about this with some of the slides that I have. All right, I love this slide, okay, you guys? So that's the Earth. It's tilted, it's rotating, and in 24 hours, if I could just kind of do a time lapse and rotate this for 24 hours, it should end up right back where it was. But let's look at the Earth. The Earth is fat. It's got an apple shape. If we had to buy a belt for the Earth, it's 24,000 miles wide at the equator. So guess what? When that 24 hours passes, the equator has to travel a lot faster. It's traveling about 1,000 miles an hour because in 24 hours, it's got to go that 24,000 miles around to end up right back where it was. But look at the rest of the Earth. As you move up, let's go up to, I guess up in Canada, they're showing another arrow. That is a much thinner part of the Earth, or if you had to buy a hat for the Earth, it would be a lot less material. And so it's actually going to be traveling slower, and it's at 60 degrees north latitude, it's traveling at 500 miles per hour. Okay, so different parts of the Earth travel at different rates, at different velocities. This is what creates the Coriolis effect. All right. Kind of talked about this. Oh yeah, and look at where Santa is, okay? Where Santa is, he's just rotating. He's not even really traveling at any velocity. It's 0 kilometers per hour. He's just rotating in a circle. So this is kind of weird, you guys. I did include a link for a Coriolis kind of thing on YouTube. You got to kind of understand this, but I'm not going to ask you like we would ask about in physics, okay? But some of the rules is that it offsets to the right in the northern hemisphere, to the left in the southern hemisphere, and it's caused because of these different velocities at different latitudes. All right, Quito, Ecuador, and Buffalo, New York share a line of longitude. They are both on 79 degrees west longitude. Quito's at the equator. Buffalo, New York is somewhere like 45 degrees north latitude. So that means that in 24 hours, they're going to line right back up. But look at the race they have to run. Quito has to run a longer race than Buffalo. So Quito, to end up right back where it was, it has to run faster, and it will go about 1,000 miles an hour, whereas Buffalo only has to go, I don't know, 800 miles an hour. Yeah, it looks like about 800 miles an hour. So you kind of understand this because you understand the races and things, you guys. You always go for the inside of the track. The horses always go for the inside rail because they want to run a little bit shorter race. If you run on the outside, far from the inside rail, you're actually running a farther distance than that horse closest to it. But obviously the Earth can't do that, and it has to happen like this because if they weren't traveling at these different velocities, the Earth would be torn apart. So it's kind of a wonderful thing. All right, and just another thing that 24 hours is a 360-degree circle, right? So it has to move 15 degrees every hour, and 15 degrees of what we call arc is a lot shorter for Buffalo than it is for Quito. So Quito has to travel much faster than Buffalo to end up at the same place 24 hours later. All right. Now, this is, you guys, again, we have to talk about a lot of things about war, and it's because of war and warlike practices that we know a lot of these things. And we know about this from basically shooting missiles. If you miss a basketball hoop, they go air ball, and, it's kind of embarrassing when you shoot a missile off and they're expensive and you miss your target by far. And so you have to have a physicist involved when you're doing targeting, or somebody who understands the basics of physics. Now, another thing that's really important is, remember we talked about that offset to the right in the northern hemisphere and the offset to the left in the southern hemisphere? You've got to look down the shaft of the arrow, okay? Otherwise, it's not going to work. So if you look down the shaft of the arrow, we're going to see the right offset in the northern hemisphere, and you look down the shaft of the arrow, you're going to see the left offset in the southern hemisphere. I'll explain more later. All right, so let's say Keto and Buffalo decide they hate each other and they want to shoot missiles at each other. Well, luckily they don't have a physicist on board, so it's a bunch of dummies with missiles. So Keto, which is traveling at an eastward velocity of about 1,000 miles per hour, shoots off its missile, and that missile is also traveling at an eastward velocity of 1,000 miles an hour. And what happens is Buffalo is only moving about 800 miles an hour, right? And so airball, expensive airball, that Buffalo has not rotated into the path. So it misses. Now Buffalo, the dummy in Buffalo with a missile, wants to shoot, hey, I'm going to get you back. And so they shoot theirs off. But that missile that leaves Buffalo is traveling at an eastward velocity of about 783, or I'm just calling it 800 miles per hour. All right, and Keto's rotating at a much faster rate, almost 1,000 miles an hour. And so what happens is that missile misses because it's not traveling fast enough to hit Keto in that eastward velocity. So both of these arrows have offsets to the right. Make sure you see this. Look down the shaft of the arrow towards the pointy end, and you can see from Keto to Buffalo, it's got an offset to the right. But now you're going to have to mentally rotate yourself, turn yourself around and look down the shaft of the arrow from Buffalo to Keto. We're in the northern hemisphere. That also is a right offset. All right, so summary of the Coriolis effect. It's caused because the Earth is a sphere and it's rotating, and that the fat part of the Earth has to travel faster than the skinny part of the Earth. What this does is causes an offset to the right in the northern hemisphere and an offset to the left in the southern hemisphere. Now actually the greatest offsets are between 60 and 90 degrees north and south latitude, because that rate of movement doesn't decrease in a linear manner, it does it in a much different manner. So the first 500 miles that we drop is between 0 and 60, and then from 60 to 90 degrees latitude is where it drops another 500 miles. Now anything that's moving latitudinally will be offset, but the things that will be the most offset are if you shot something from the equator to Santa's workshop at 90 degrees north latitude, oh my gosh, would it be offset? Because it's traveling the greatest distance you can latitudinally. Okay, and that last part, it's a little complicated. It's a physics thing. Watch the videos that I put up, or the video, or go onto YouTube and find out. But you can actually see that it actually is moving a straight line, but straight lines on a spherical surface look curved. All right, now you guys, I have movies for the stuff that's a little bit more difficult, and you're gonna have to watch these movies. So in order to understand this vertical atmospheric circulation and the wind belts and boundaries, you need to print out 2 of those diagrams that are in your weekly folder, and then watch those videos. And remember, I put them up on YouTube also, just in case you're not able to see them in the folder. And practice, and you guys, use my hints, because oh my gosh, this is so easy. It's a lot easier than it looks. All right, so you are going to figure out how to do that vertical atmospheric circulation, and that's on the outside of this. And then the next one you learn is how to do wind belts and boundaries. And so you can see the different wind belts. And remember, these things are symmetrical about the equator, and so that makes it easier. The other thing you need to remember is that, remember what I said, it rains every day at the equator. Oh my gosh, that's how I start all of this. And so that's going to be an area of low, because in lows you have clouds and rain. In areas of high you have sunshine and it's dry. Okay, so if you kind of remember these, you guys have lots and lots of points on the exam and on those in-class assignments. All right, so the lows are at the equator, and we also have a subpolar low. Remember, it rains every day in Seattle too. And the highs, if you want to go bake yourself in the sun, go to the tropics, a subtropical high. Go to Cabo San Lucas. The poles are also areas of high, and you might say, well, wait a sec, how do I get so much ice in Antarctica? You get so much ice in Antarctica because it, until recently, wasn't melting, and so you had 25 million years worth of 2 inches of precipitation a year or something like that. So it's really not an area of a huge amount of precipitation. All right, don't really worry about this. The book talks about this. I'm not going to ask you guys about Hadley, Farrell, or polar cells, but in each of the hemispheres we do have 3 distinct circulation patterns, one going from the equator to 30 degrees, the other one going from 30 to 60 degrees, and the final one going from 60 to 90 degrees. All right. Remember to look at that video, you guys. You're not going to make it without that video, because what it's going to do is take this information and make it really simple for you. You guys have to do it. It's worth a lot of points on the exam. It's 2 in-class assignments. You just got to do it, and just do it, and listen to my hints, because I swear I don't have this stuff memorized, but I can draw it out every single time because of what I call basic principles. All right, so you're going to have to produce something that looks like this on your in-class assignments and on the exam. And we can have them on 2 separate pictures or not, I don't care. All right, so lots of different ways at looking at that. Now, the other thing I asked you to learn, and that's on the video too, are the wind-built boundaries, the boundaries. And I told you the stories, the doldrum, also known as the intertropical convergence zone. You don't have to worry about dying if you get stuck there in that windless zone because it rains every day. Told you the sad story about the horse latitudes at 30 degrees north and south latitude. That's the dry latitude. So if you get stuck on a boat there, that's not good news. All right, and finally we're going to have the polar front between 60 and 90 degrees north and south latitude. And that's actually kind of not a nice place to get caught either because of the storminess.